Hi folks, today we're going to continue on with our discussion of rational functions. We're going to do a couple more examples. We're going to talk about transformations of rational functions real quick, and then we're going to get into slant asymptotes. But first let's talk about transformation of functions. Yesterday we talked about the reciprocal functions. We talked about f of x is equal to 1 over x, and we also talked about f of x is equal to 1 over x squared. And I'm actually going to use a different color here so it stands out a little bit more. So if we were to graph the function f of x equals 1 over x squared, right? I know that I have this point here and this point here. I know it's symmetrical about that y-axis. This is my asymptote, right? Because or x can't be equal to 0. And so we end up with a graph that, whoops, does something kind of like this. Ends up doing this. And does this. That's my really rough graph sketching ability here. That's curved more. Right, and that's what our graph kind of looks like. It should be a little bit more symmetrical, but you get the general idea of the shape there. And so let's talk about taking that same function, or taking that function and performing a transformation on it. So now I have 1 over x minus 2 squared plus 1. So if you just saw this function here on the right, you should say to yourself, okay, well that kind of looks like 1 over x squared. It's just been shifted. And remember what happens when you do horizontal shifts and vertical shifts. When you're doing a vertical shift, you're just tacking a number on the end. So this plus 1 on the ends means I'm doing a vertical shift of 1. So everything is shifting up 1 unit. This x minus 2 in parentheses tells you it's a horizontal shift, and you're going the opposite direction of the sign. So because it says x minus 2, that means we're going to be shifting to the right 2. So I'm going to take everything that I have here and shift it over to the right 2 units, meaning that my vertical asymptote goes from 0, from x equals 0 to x equals 2. I also had a horizontal asymptote at 0, but that's also going to get shifted, and that's going to get shifted up 1 because my entire function is getting shifted up 1. Oops, so that would be right, if I could draw this a little better, that would be right there at y equals 1. And so what happens then is our function ends up, I had this point 1, 1. It's now up at 3, 2, right? Because I shifted over 2 and up 1. Same here. I had a point at negative 1, 1, and that got shifted over. So that's at 1, 2. And so now my new function is here. Oops. And it should be going through that point and there. Okay, so just a quick little demonstration on what happens when you're transforming rational functions. Very similar to what we did with quadratic functions and all of those different things. Parentheses means you have a horizontal shift, you're going the opposite direction. Number tacked on the end means you have a vertical shift. Okay, so pretty straightforward there. I just wanted to do a quick review of that. Let's, though, talk about another graphing another rational function. We did one yesterday that was pretty basic, but let's go through the steps of this one. Remember, the first thing that we're going to figure out is if we have any sort of symmetry. Okay, so do I have symmetry? Oops, trying to find a good pen here. See if I can move this a little bit. Okay, so do I have symmetry? Oh, that's not what I wanted to do. Okay, here we go. Just trying to figure out my pen here. Do I have symmetry? Well, if I do f of negative x, I substitute negative x in for x, so I have 3 times negative x squared over negative x squared, oops, minus 4. There should be a minus there. Minus 4. And when you square a negative number, you just get back what you started with. So you have 3x squared times x squared minus 4. So I will have y-axis symmetry. That's the first thing. Okay. The second thing we're going to do is find our y-intercept, which is just finding f of 0. That means just plugging in 0 for x. So everywhere I plug in 0 for x, I end up with f of 0 is equal to 0. So I know my y-intercept will be at 0. My x-intercept is where f of x is equal to 0. So remember, in order for the whole function to equal 0, that numerator has to equal 0. So if I say, well, 3x squared is 0, that tells me that x has to also be 0. Okay, so my y-intercept, my x-intercept, that all happens at 0. I'm just going to go on to the next page where I have a little bit more room. And so far we know we have intercept at 0. We know we have y-axis symmetry. Let's talk about vertical asymptotes. So vertical asymptotes, that's where our function would be undefined. We can't reduce this function at all, so we're not going to have any holes in this graph, right? Because this is the only representation of this function that we can have. So I'm just going to take that denominator, set it equal to 0. This should be pretty straightforward. X minus 2 and x plus 2. So you know that at x is equal to plus or minus 2, you are going to have vertical asymptotes. So let me go ahead and put those in. I'm trying to find a better color that works on this screen, but we'll leave this for now. Those are our vertical asymptotes. Let's talk about horizontal asymptotes. Remember that when your degree is even, or is equal to each other, excuse me, on the top and the bottom, then you're just taking those coefficients. So your coefficients would be 3 over 1 or 3, which tells us we have a horizontal asymptote at y equals 3. Okay, so those are our asymptotes. That's our y-intercept. The only other thing we can really do is plot points beyond and between to get an idea of the general shape. One thing that we can use to our advantage is that we know that this has y-axis symmetry. So whatever I do on one side of my y-axis, I know is also going to work on the other side of my y-axis as well. So at negative 3, actually let me do this, at negative 4, negative 4, negative 3, and negative 1. Let's do those. At negative 4, if I plug negative 4 in here, I end up with 4. At negative 3, I end up with 5.4. 27/5 it comes out to be. It's about 5.4. And at negative 1, I end up with negative 1. So let me see if I can get a better, maybe pink will work better here. So when x is negative 4, I'm up here at 4. Maybe I'll just go with black. That probably is going to be the best one. Okay, there we go. When x is negative 3, I'm up here at 5.4. So again, because I have y-axis symmetry, I know that I will also have a point here, and I'll have a point here. I also know that at -1, I'm at -1. And again, because I have y-axis symmetry, I'll have that point there as well. So you can kind of see what's going on here. I end up with this graph where I'm approaching my vertical asymptotes, but I don't ever touch them. And so here, right, I end up with that. And those are arrows on the ends of my graphs there. I know it's kind of hard to tell. But you should have arrows on the end because it does continue on. Okay, and that would be a sketch of that graph. So use that symmetry information you have to your advantage. That way you don't have to make a larger table. This is really all you need when you're finding your values there. Okay, I'm going to end this video there. We'll start the next video talking about slant asymptotes.